Hi, my name is Trevor Asaf. I'm here today with Nick Dard and Kyle White. We constitute Team A9, and we are going to discuss nested quantifiers. So nested quantifiers are quantifiers in the scope of other quantifiers. For example, let's consider the case universal x, existential y, q of x, y, where q of xy is equivalent to x minus y equals 0. Now, this basically says, if we break it down, for all values of x, so for each value of x in our domain of discourse, there exists some complementary value y, such that x minus this value of y is equivalent to 0. Now, to illustrate the nested structure of this statement, we can rewrite it, in the following way. Bear with me for a moment. Existential y, q of x, y. Let's set that to p of x. Great. Now we can use this to rewrite the original statement as universal x, p of x is equivalent to universal x, existential y, q of x, y. Now, here, in this example, we've consolidated this clause of our statement into this variable. Basically, the left-hand side of this equation says, for all x, p of x is true, and that's equivalent to saying, for all of x, this statement is true, where that equals p of x. Now, this illustrates the fact that this quantifier is outside of the scope of this quantifier, illustrating the nested structure. So, as with all quantification, the same rules of logic on quantifiers and predicates apply to nested quantification. Let's consider the example where we have universal x, universal y, universal z, where our predicate is the associative property. X times y times z equals x times y times z. So our predicate is very familiar to us. That is the associative property in action. Now in our quantifiers, we find universal x, universal y, universal z. If we translate this to English, it says, for every element in x, and for every element in y, and for every element in z, our predicate holds true. Now, intuitively, this makes sense. The associative property always holds true. Therefore, no matter what variables no matter how you quantify the variables, it's going to be valid. Now, let's take a quick detour and explore a different perspective of nested quantifiers. You can think of nested quantifiers not as quantifiers per se, but as nested loops, to put more of a programming lens on this concept. So let's consider universal x, universal y, p of x, y. Now, in order to check to see if this statement is true, we can iterate through each value of x in our domain of discourse. Each value of x. And then for each value of x in our domain of discourse, we can then iterate through each value of y, all the while checking to see if our predicate p of xy holds true. And then once we finish once we finish checking all the values of y for a given value of x, then we would iterate, we would progress to the next value of x and continually check through all the variables in x until we excuse me, until we finish iterating through the domain. Now, if all combinations of x and y hold true, then this statement will be true. Otherwise, if you find at least one instance where it's false, then that statement will be false. Now, going back to this example, we can easily say, right, that we can rewrite the order of the quantifiers. Instead of universal x, universal y, universal z, we can rearrange them. For instance, universal z, universal y, universal x, or perhaps universal y, universal z, universal x. There are a couple other combinations that we could choose. Now, the point of this is if you apply the same logic that we used to think of nested quantifiers as nested loops, this transformation suddenly makes sense. So if we iterate through each value of x, and then for each value of x, we iterate through each value of y, and for each value of y, we iterate through each value of z, then we will check to make sure that this predicate holds true for all combinations of the variables x, y, z. So intuitively, it makes sense that no matter what order of quantifiers you choose, no matter what order, no matter what comes first or what comes last, as long as each quantifier is the universal quantifier and all the variables are the same, then then you can rearrange the order of the quantifiers and achieve the same result. Now let's examine nested quantifiers using a mix of universal and existential quantification. So in this example, we'll have universal x, existential y, p of x, y. And this would be read, for all x, there exists a y that satisfies predicate p of x, y. Now, in our interpretation, we are going to assert that p of x, y is equivalent to x plus y equals 0. Or x, y are all reals. Okay. Now, if we apply this interpretation to this statement, we see that this statement is true. So, again, it says that for all x, there exists some y, such that x plus y is equivalent to 0. Therefore, each x has a corresponding y whose sum is 0. We know that given this relationship, this statement will hold true. Now, consider the same predicate, but with different quantifiers. So instead of universal x, existential y, we're going to flip that. So now it's existential y, universal x, p of x, y, where p of x, y is the same predicate that we defined earlier. Now, how does the meaning change? Does it change? So now if we translate this to English, we find that it says, there exists some y such that for all x in our domain of discourse, our predicate is satisfied. Now if we think about this intuitively, it says that there's a particular value of y that satisfies that no matter what value of x you pair it with, the sum of y and the sum of an arbitrary value of those x's will equal 0. And that doesn't make any sense because, again, going back up here, we know that the only time y plus x is going to be 0 is when y equals negative x or x equals negative y. And that sure doesn't hold true for multiple values of x or multiple values of y. Therefore, this statement, given our interpretation, is false. So these two examples have shown the importance of the order of quantifiers and how the meaning of a statement can change and even become false when the order of quantifiers changes. Thank you for your time. Again, we are Team A9, Trevor Asaf, Kyle White, and Nick Dard. This is a lecture on nested quantifiers. See you next time.